We're living through a remarkable moment in planetary science. For the first time, we have rovers crawling through ancient lake beds and river deltas on Mars, drilling into rocks, and returning data that lets scientists read the planet's chemical history. The question people keep asking is simple. Have we found signs of life? The short answer is, not yet. But the evidence collected so far makes Mars a far more promising place to look than anyone expected a generation ago. In this video I'll walk you through what's been discovered, what those discoveries actually mean, and why the next big step, returning samples to Earth, is so important. Start with context. Life as we know it leaves traces, patterns in chemistry and minerals that are best explained by biological activity in watery environments. On Earth, microbes change mineral chemistry, leave organic molecules, and create textures in sediments that point to life's processes. Mars scientists therefore look for the same kinds of fingerprints, organics preserved in rocks, mineral associations that form in water, and sedimentary structures that indicate long-lived lakes or deltas. Two rovers in particular have reshaped that search. Curiosity, operating in Gale Crater, has found an impressive suite of organic molecules in 3.8 billion-year-old lake sediments, the most complex and abundant organics detected on Mars to date. These aren't trivial fragments. Some are long-chain carbon compounds that on Earth are associated with biological materials and preservation processes. Curiosity's findings tell us that the ingredients for life and their preservation were present in the ancient Martian rock record. Perseverance, exploring Jezero Crater, a paleolake and delta, has recently delivered what many scientists call the most intriguing set of observations yet. In a 2024 rock nicknamed Chayava Falls and other nearby outcrops, the rover observed curious leopard spot textures and specific mineral assemblages, including iron phosphates and iron sulfides in layered mudstones. On Earth, such combinations commonly form in waterlogged, low-oxygen environments and are sometimes associated with microbial activity. That makes these outcrops exceptionally high-priority targets for the life detection question. Importantly, NASA is clear that these findings do not prove life. There are non-biological ways to make similar minerals and textures. But the discoveries mark a significant increase in the likelihood that Mars preserved environments and chemistries favorable for life. Let's step back and unpack what these statements actually mean in practice. Detecting organics on Mars answers the question, are the chemical building blocks present? Yes. Detecting minerals that form in water answers, was there liquid water, perhaps long enough to support life? Again, yes, in many places, but the crucial leap from habitable conditions existed to life actually arose there requires more than one line of evidence. That is because abiotic chemistry can produce organics and certain minerals. Meteorites that continually rain down on Mars can also deliver carbon-bearing compounds. In short, organics alone are suggestive, not definitive. This is why context matters so much. On Earth, when geobiologists declare evidence for ancient life, they typically show a stack of converging clues. First, a sedimentary environment that concentrates and preserves organics. Then, specific isotopic patterns in carbon, as life preferentially uses lighter carbon atoms, leaving a distinct signature. They also find suites of molecules that show biological fractionation, and tiny microtextures within the rock that closely match the size and shape of known microbial structures. When multiple independent lines of evidence, the geology, the chemistry, and the morphology, all point the same way, the case becomes powerful, much like a detective building an airtight case from different sources. On Mars, we're beginning to find places where several of these lines overlap. In Jezero Crater, for example, the Perseverance rover has found a surprising diversity of complex organic molecules within the sediments of an ancient river delta. Finding the right chemicals in the right geological setting is a huge step forward. This is what makes the current discoveries so compelling, even if they are not yet proof of biology. Another fundamental reason researchers urge caution is instrument capability. Rover instruments are incredibly sophisticated mini-labs, but there are fundamental limits to what can be done on a Martian rover. They face strict constraints on power, size, and weight, and cannot perform the multi-step sample preparation that is routine in labs back home. Some analyses, like extremely high-resolution molecular separation, which can tell if molecules were made by life, or ultra-precise isotope ratio measurements to definitively rule out geological processes, require large, power-hungry equipment. These complex cross-checks using multiple independent laboratory techniques are currently only possible in full-scale Earth laboratories. That's the main scientific reason the community agrees. To reach near-conclusive evidence, we will very likely need samples returned to Earth. The ambitious Mars sample return mission is designed for exactly this. It will allow pristine samples to be analyzed by dozens of independent teams in labs worldwide, providing the rigorous cross-checking that such a profound discovery demands. So where does that leave us today? Practically 3 important takeaways. 1. Mars had environments in its deep past that were habitable by our standards. This is no longer debated. For potentially hundreds of millions of years, liquid water was present on the surface, energy sources existed from the sun and geothermal heat, and the chemical ingredients for life persisted. This wasn't a fleeting moment, it was a stable, long-lived era of potential. Second, the discovery of organic molecules. These carbon-based compounds are the fundamental building blocks of life as we know it. Perseverance has confirmed that molecules ranging from simple to more complex have been preserved for billions of years in ancient lakebed sediments. This is a crucial finding, as these materials are typically fragile. It tells us that the raw ingredients for life were present in Jezero crater, whether they formed there or were delivered by meteorites. Their preservation is a vital piece of the puzzle. Third, the rover has identified intriguing rock textures. In some of the oldest rocks on the crater floor, Perseverance observed distinctive patterns and high concentrations of iron-rich minerals. On Earth, similar structures can be created by microbial communities. While these can also form geologically, their resemblance to terrestrial biosignatures makes them prime targets for investigation, demanding we take a much closer look. But what would convincing evidence look like? The scientific community has a high bar, demanding multiple independent lines of evidence. Ideally, a return sample would contain complex organic assemblages with isotopic ratios suggestive of biological processing. Life, for instance, prefers lighter isotopes of carbon. We'd also need to find microstructures consistent with microbial mats or filaments, all found within an unambiguous sedimentary context that preserves the sample in situ. Meeting those criteria would not be easy, and scientists would subject such claims to intense cross-examination, following the principle that extraordinary claims require extraordinary evidence. Teams around the world would work to verify the findings and challenge every non-biological explanation. This rigorous process is exactly how science should work. This level of analysis is impossible for a rover, which is why sample return is not just a luxury, it's central to resolving the life question. The Mars Sample Return Campaign, a partnership between NASA and ESA, is a multi-stage mission of unprecedented complexity. It aims to collect the samples cached by Perseverance, launch them off the Martian surface for the first time in history, and ultimately return these precious materials to Earth. These returned rocks would be examined by the full power of Earth's laboratories, using techniques we can't put on a rover. We could use instruments the size of buildings to map their chemistry atom by atom. That's why agencies are pressing ahead with complex mission architectures despite the technological and political challenges. The scientific payoff could be transformational, forever changing our perspective on our place in the cosmos and potentially answering one of our oldest questions: are we alone? Before we wrap up, let's be candid about the timeline and expectations. In the search for extraterrestrial life, the principle that extraordinary claims require extraordinary evidence is paramount. So a declaration of "we found life" wouldn't come from a single press conference. It would be the culmination of a painstaking multi-year process, requiring rock-solid confirmation from multiple independent labs around the world. This rigorous process is essential to rule out any possibility of terrestrial contamination or instrumental artifacts, ensuring the discovery is truly Martian. So, we should expect incremental progress. This means better contextual mapping by rovers, providing a geological backstory for every rock. It means more precise in-situ measurements that can sniff out complex organics. And then, the grand finale, the Mars Sample Return Campaign. This audacious mission, a joint effort by NASA and ESA, is a complex interplanetary relay race designed to bring the most promising samples back to Earth using a lander, a fetch rover, and the first-ever rocket launch from the Martian surface. In the meantime, the discoveries already made are fundamentally altering the mission on the ground. For example, identifying ancient river deltas like the one in Jezero crater has become a top priority. Scientists now know these are prime locations where the ingredients for life could have concentrated and, crucially, where their chemical signatures might be preserved in fine-grained clay minerals. This knowledge directly informs which rocks are worth the time and energy to drill and cache for future return. In short, Mars today looks more like a planet that had both the ingredients and the right places to preserve them than we thought a decade ago. That doesn't mean the planet was teeming with microbes. We don't have that proof. But it does mean the search for ancient Martian life is now sophisticated, evidence-driven, and closer to a definitive answer than ever before. If you want the short takeaway, we're seeing organics, water-altered minerals, and sedimentary environments that preserve chemistry, all of which make Mars one of the best places in the solar system to search for ancient life. But the final compelling proof will most likely come from those samples returned to Earth. Why? Because no rover can carry the sheer analytical power of our planet's best laboratories. We're talking about building-sized instruments that can map the atomic composition of a sample without destroying it, and clean rooms more sterile than an operating theater. Only here can we deploy the full arsenal of modern science to make a claim that would rewrite the textbooks. If you found this deep dive helpful, subscribe for more careful breakdowns of space news and the real science behind the headlines. Thanks for watching. Subscribe for more careful breakdowns of space news and the real science behind the headlines. Subscribe for more careful breakdowns of space news and the real science behind the headlines.